Good morning, students. I hope everybody's doing well today. We're in that kind of interesting temperature range where it's cold outside, but it's still warm inside. So we back to the AC heat uh, debacle that we have living in Houston. But I always like to talk about the weather because it's always something that impacts us that maybe is not so stressful. Um, Today, what we want to do is cover volumes of solids of revolution with a particular method called the disk method and the washer method, which is just an adjustment of that. And then there's just a little short section on volumes by cross sections, which are simple to understand. I think you'll find that there's a lot of illumination in what we do today. We're moving from the regions that we talked about last class, and we're going to start revolving the region. But before I do that, I made up another example similar to the one we had last class that I thought had so many good ideas in it. When it comes to doing these inverse trig problems with the integrals, uh, my feeling is that if you can work out the ones that have the most kinks in them, then the rest of them will be easy. So I made up another problem that I just want us to work through as a warm up. So let's go ahead and look at that. So what I did, ladies and gentlemen, is I just took the same construct that we had with the other problem. Remember the way I initially factored it, it was too hard to keep up with the pluses and the minuses. So I just said, well, let's try this way. So I wanted to just make up another example. And again, I made sure that when I constructed this, that we actually get a real number. We don't have an improper integral because the integrand would become infinite upon anti-differentiation. So I thought we would just go through this to get another good example of how we can put all the pieces together. So notice when you look at this example, like the last one, we have what could probably be an inverse sine form, but we have some other stuff. So we're going to approach it the same way and do the same technique. But the way I've set this up, we'll just have a little bit more arithmetic to do, but it will be very reasonable. So first, just like we did before, we'll set u equal to 10x minus 4x squared. And then let's look at the du. And this will give us a 10 minus an 8x. So you're seeing I'm doing the same thing with the negative signs. So I thought that was an interesting example that Dr. Larson had in our WebAssign. So now we're going to take the same approach. What we can see here is that we do have the 8x, we don't have the negative. So, or let me silence my email. That way we don't get dings during the lecture. And so we'll take the same approach that we did before, but not overdo the parentheses that make us crazy. So now we can say, okay, let's go ahead and put in the negative to offset the negative that we need for the 8x. And then, of course, now with the negative on the outside, we'll have a plus 5. So we have an equivalent integral. And it's better than using the parentheses to factor. I always like to try new things, but let's face it, a new method isn't always good if it makes the problem harder. So we'll stick with this. So again, this is really the main construct of the problem. Once you get to this, it's pretty much downhill. There's a lot of work to do, but notice we have the 8x and we have the minus 5, so these are equivalent. Now, the next thing we need to do, because we're thinking of the Cal1 part of the integral, is that we want to introduce the 10. So we can add the 5 to the 5 and subtract the 5. And that will give us the 10 that we need. And then the other part will just become the inverse sine portion. So let's go ahead and write that in. So what I'm going to do here, and I'll put this in red, add 5, subtract 5. So when we add the 5 to the 5, we get the 10. And that gives us what we need here. And then, of course, we have to pay for it right there. So again, this approach makes it the easiest to reconstruct the integrand in a way that it's very doable. So this is the part I want you to practice. And once you have this down, then like I say, it's very straightforward. So now we have the two pieces that we can contend with. So let's go ahead and break up this first piece, which is the Cal1 integral. So we have the negative 1 to 2 of, now we'll go ahead and move this upstairs because this is the add 1 divide by the new power integral. We like these. Always fun to do the power rule for antiderivatives. So the negative 1/2, and then of course the negative 8x plus 10 dx. So we see that the first part here just gives us our standard calculus 1 integral like we had with the last problem. Now notice we have the negative, so we'll have plus 5. We'll have the integral 1 to 2. But of course now we're going to have the dx upstairs, which we'll have to do a little bit of work on. But we clearly know that we're going to have to complete the square here in order to use the inverse sine form. So I'll go ahead and start reconstructing this. So first, and use brackets instead of the integral sign or the square root sign. That's so hard to draw. And so now we can do a negative to make this monic, a negative 4 x squared. And then we have the minus 10 over 4 x. So notice when we do the negative times the negative, those absorbs the 4, that will absorb the 4s, and then we get the positive 10x. So that's the correct algebra there. And now what we want to do is take half of this. When we take half of this, the 2 divides into the 5. So that gives us a negative 5 over 4. So we're going to square that. So that'll be 25 over 16. And then, of course, we want to subtract that off, pay for it. So this all goes in the parentheses and then the 1/2 on the outside. So let me just make a little comment here. We do the negative 10 over 4 times the 1/2. That is, we take half of that and we square it. And of course, the 2 divides into the negative 10. So that's a negative 5 over 4 quantity squared. So the so-called magic number to complete the square would just be 25 over 16 as we have here. So again, the algebra is a little bit more complicated than we had with the last problem, but it's the same technique. Okay, so we can clean this up. So now this one will get to the finish line a lot faster, obviously. So now we have the negative here. So add 1, it's table ready, add 1, divide by the new power. So we get the 1/2, division by 1 is just 2 over 1. And then of course we have 10x minus 4x squared to the 1/2. And then we have our limits of integration 1 to 2. Okay, so that's the easy integral. Now over here, we'll just go ahead and clean up this algebra. Now notice we want to flip this around. So we have in here the negative 4, here the negative. So this is going to give us a 25 over 4 because the 4 will absorb into the 16. So we'll go ahead and write our fraction bar. And we'll have our dx. So first off, we get the 25 over 4. And then what's left? Well, now we've got the minus 4, and then we have the perfect square here. And this is x minus 5 over 4 quantity squared, as we see from right here. Okay, and then notice we want to pull in the negative 4 here into the square, so we'll make that into a 2. So we'll have minus 2 x minus 5 over 4 all squared. So when you look at this again, this is the minus 4 times this, but we want to bring the 4 into the umbrella of the square, so we have a u. So that 4 here becomes 2 squared. So when we square this out, we have the 4 and we have this when it's expanded. So the algebra is correct. So at this point, what I want to do is, you're thinking, well, this is just a definite integral, Professor Ron. I don't care that it looks terrible, but let's clean it up a little bit and then make the algebra a little bit simpler. So now here we have the negative 2. We'll go ahead and look at this. And we can substitute the 2. So that'll give us a 20. And then the 2 here, 4 times the 4 minus the 16, 1/2. Got lucky with the perfect square there. And then with the 1, we just get 10 minus 4 to the 1/2. One to 2. Now at this point, we see we have the 4 here, but we can get a common denominator here. And then of course the 2 will absorb into the 4. So let's go ahead and get a common denominator. This takes a little bit more algebra here just to make it look neat. And now with the common denominator here, notice we'll have a 4, but the 2 will divide into that. And then of course we square it. So we'll have minus, we'll have the 4 here, the 4x minus 5 quantity squared. And then we'll have the 2 over the 4, which gives us the 1/2, and then we square it, and that gives us the 4. So that's the cleanup that I was talking about that will help us to make the algebra a little bit simpler. So again, note when we get the common denominator, we get the 4x minus 5, and we have the 2 over 4. That's 1/2. When you square it, you get the 1/4. And so we can remove that from the square and see, this is kind of like doing the derivations we did the first day. So now we can clean this up and be on road to the finish line. So minus 2. Of course, here we have the square root of 4, which is 2. And here we have the square root of 6. Now we've got plus. Notice we have a 4 in all of this. So that's basically the factoring that, we get the square root of 1/4, which is 1/2. So the 1/2 comes out. So now we have the 1/2 downstairs. And what's left? 25 minus 4x minus 5 quantity squared to the 1/2. And then of course we have the dx here. Now we can adjust this because now it's nice and user friendly. So we can say, okay, well, we've got an a here of 5, and we have a u of 4x minus 5. You're thinking again, we could have saved ourselves some time to avoid some of this algebra, but I think this is good practice to make it look a little bit easier and then easier to evaluate. But again, you still get the same answer. And du will just be 4 dx. So now, of course, we need the 4 here, so we can put in the 4 here and then pay for it here to make this table ready. So that would be the adjustment we would need here. And then, of course, this 1/1/2 is going to flip and come up here and absorb one of the 2's in the 4. So now, almost done. Run the -2 through. So this is a 2√6. And then a -2 times a 2 minus 4. Well, that was the easy part. And then we have plus 2, again, 1/1/2 times 5/4. And this is table ready. So this gives us the inverse sine of u 4x minus 5 divided by a, which is 5. Evaluated from 1 to 2. So if you think about the problem we did before, this is the same thing. We just had a little bit more arithmetic in this part, but the approach is exactly the same. So now we get 2√6 minus 4. Now, of course, here this will just give us a 5/2. And now we can substitute the 2 into the argument here. So that would give us an 8 minus a 5, which is a 3/5. So inverse sine of 3/5. And of course, that's not on our unit circle, so we just leave that alone. And then for the lower limit, we'll have the 4 minus the 5/5. So that'll be a -1/5. And of course, remember, the inverse sine is odd, so the negative can factor if you like, just to make it look a little neater. Remember, inverse sine is odd, so the negative factors. So this will give us 2√6 minus 4. And then we can just go ahead and multiply this out. Of course, notice that the negative will extract because odd function. And then as we look here, we'll have minus 4 plus 5/2 inverse sine of 3/5. Now minus minus plus, oh, of course, that 5/2 comes around to distribute. We don't want to leave out the 5/2. It's very important. Inverse sine of 1/5. So when you look at this problem, again, it's the same as the other one. And I wanted to make the point that when you're doing these inverse trig form integrals, again, usually it's very easy to see, well, that's going to be the inverse secant, or that's going to be the inverse sine, or that's the inverse tangent. But sometimes the two integrals are combined into one. So we needed our lecture on the inverse trig functions to do this problem, but I wanted to emphasize the fact that if we just simply focus on the x term with the negatives and leave out the constant term, it makes it much easier to navigate the algebra. And so basically, this problem kind of contains all of the bells and whistles that you need to do these types of problems: the adjustments, breaking up the two integrals, and using the integral forms. But again, I thought it was interesting because I tried to fidget this so that the integral came out to be a real number, but I like the numbers, even though we can't use our unit circle on these particular functions. We still have an exact answer, and that's the goal. Of course, the WebAssign will often say give a decimal approximation, and that's just throwing in a little variety. But again, when that I like how one of you said that calculator pad comes out, that's when you type the exact answer. And so anytime the pad comes out, you can do an exact answer. So again, this is just a review to give you another good example of how we utilize the technique that we talked about in the last class. So make sure that this is comfortable. I have another conference hour today. So if you want additional description of this, please come by and we can talk about that. Okay, so now what I want to do is look at some examples that deal with the solids of revolution. Now, what I want to do is look at an example that kind of covers several different problems. So in this case, we'll say 7.2, we'll say disk method, disk, washer methods. And then at the end, I'll say a little bit about the cross section. The washer method is just an adjustment of the disk method, so there's nothing new. And this will be to compute volume of, like doing an area before, compute volume of a solid of revolution. Now, the idea here is simple, ladies and gentlemen, just like the idea we had with the areas. We just take the definition of the Riemann integral and just, if we want areas bounded by curves, we take a difference of two integrals and then push it together, and we've just got the one integral using the linearity of the Riemann integral. So we find that that definition is very useful. Now, what we want to do is think about how we could take a region and revolve it to create a solid and then come up with the volume, and it's very simple. So let's look at an example. I'll do a couple of these where we have a different axis of revolution. So our region for our first example will be the one bounded as follows. Y equals the square root of x. Y equals 0. Of course, that's the x-axis. And then the vertical line, x equal 3. And for the first problem, we'll just call this A. We want to revolve region about x-axis. And then, of course, just like I've written here, we want to compute volume of the solid. So when you think about this construct, you can think about like a sphere. A sphere is a solid of revolution if you think about rotating half of a circle, basically. When you just rotate it around, you form the sphere. And so you're thinking, well, you can use that construct to derive a formula for the volume of a sphere. And that's exactly what you can do. What's amazing is that the Greeks came up with all these volumes with their own idea of infinitesimals that we did not enjoy, that we don't enjoy, that because we use Newton and Leibniz discovery. So the Greeks had some way of intuiting mathematics that really went way beyond what we do. And so it's nice to see that we have the utility of the calculus to do these problems. So what we can do in this case, just like we were computing an area, is get a simple sketch. It's always nice to have a visual of this. We'll have to draw this region a couple of times as we have a different axis of revolution. And so now we'll just mark this off. 1, 2, spread this out a little bit more since we have the room. 1, 2. And so we have y equals 0. And then the vertical line, x equals 3. And then, of course, we'll have the square root of 3 where the square root function intersects with x equal 3. So we can sketch that. So of course, this just goes on. So here, we'll have square root 3, and here we have 0 to 3. So the idea is that when we think about this process, it's going to depend where the region is relative to the axis of revolution. So now the region, of course, this will be the same in all these examples, will just be this. And so what we want to do is to revolve about the x-axis. Now the idea here is because the axis of revolution abuts the region, we're going to think about partitioning just like we did with the area and take one rectangle and revolve it. So for instance, we'll have X living between, no symmetry here, even though we use symmetry so much, it's almost indispensable. We'll take an X and we'll just draw in a rectangle here. Now, the idea is we can do this for every element of the partition and generate a disk, so to speak. So the idea is, this is why we call this method the disk method. As we rotate, we create a disk, a circular disk, and we know the area of the circle. And then of course we know the thickness is delta X, but in the limit, the delta X becomes the dx. So basically, all we need to do when the region abuts the axis of revolution is look for our radius function. And when we just have one, we call it R. So we're just going to say this is R equals the square root of X. So the distance here from the axis to the curve is just given by the function square root X. And of course, the algebra tells you how to actually define that dimension. And that's why a picture is always really nice. And so then you think, well, how do you find the volume of the disk? Well, it's the area of the circle times the thickness. So this implies that the volume will now be, again, what always had that pi r squared, so you can go ahead and factor the pi. We want to integrate from 0 to 3. And then we want to integrate the area element times the dx. So this will be the area element, which is pi r squared dx, giving us the volume. So now what we're thinking here in general, we'll think volume equals pi. For instance, if we were using x as the independent variable, squared dx. So this formula, obviously, like when we're doing areas, has to be flexible. So maybe we need the independent variable y. But in this case, we have the simplest possible situation. That is, we just generate a bunch of disks, and we just stack up the disks like a bunch of pancakes, and let the limit, in this case, the norm of the partition, go to 0. And that limit gives us the Riemann integral. So students find this to be fairly simple as long as they can get a reasonable picture of the region. So now we have the volume using our disk method. Remember, and here's another important part that we need to know about the disk method. The disk method, the rectangle will always be perpendicular to the axis of revolution. So we want to think of a rectangle that aligns itself perpendicular, so perpendicular to the axis of revolution. So that's one of the hallmarks of the disk method. And then of course it will be one of the attributes of the washer method. So now very simple integral. So we get pi integral 0 to 3, squaring the radical just gives us x dx. And so we have pi x squared, add 1, divide by the new power. Don't we wish all of our integrals could be this easy? So we have pi over 2. And now we can substitute 3, but of course the lower limit 0. So we're going to get 3 squared minus, sometimes I'll just leave out the lower limit as long as we know that it's annihilated, just ignore it. And so of course now this will just give us a 9 times a pi over 2, so 9 pi over 2. So what we generate here is a little gumdrop, so to speak. When you revolve it, you have like the solid of revolution that looks like a little gumdrop, you know, or like if you get Valentine's candy, the little drops that have the gooey center that not everybody likes. So you can think as an engineer, you can design your own solids of revolution and be very creative. And then your boss says, well, what's the volume? Well, you'll say, well, let me just use my disk method or something. So these formulas are very useful for modeling projects and things. So there is a creative bit about these. Now, what I want to do is to vary this a little bit so we can talk about the washer method. Now, the next example, we're going to take the same region. So we're going to take the same region, but we're going to vary the axis of revolution. So here's what I want you to do. This is going to be B. So I want you to go, let's go ahead and draw the same region. Okay. So let's see here. We've got our x-axis. So the same region that we had before. So I want you to see how varying the axis of revolution does obviously change the solid. So we'll have a 1, 2, 3, spread it out just a little bit. So we have x equals 3. And of course we have y equals 0, which is the x-axis, and we can go ahead and mark off here. So draw your square root function, goes like that. So here's our region. Now, in this particular problem, we want to revolve this region. So same region as before. So I'll just say y equals square root x, x equals 3, and y equals 0. That defines the region just like we had before. And what we want to do is revolve region about the y-axis. So now when you think about this and you think about the problem we did before, let me just, I wanted to make sure I put that little arrow around. So we want to revolve about the y-axis. Now, again, when you think about that, this is where we have a little change. We applied the disk method twice. So notice here, we can go ahead and mark off the value of y here. That's square root 3 and that's 0. So we can see that y lives between 0 and square root 3. And now, of course, if we're looking at equations with y independent, we can square this and have x equals y squared, kind of looking at this from left to right. So now what we want to do is revolve this region, but notice the region here does not abut the axis of revolution throughout the region like we had with the first example. So what we can do is let's just take a y here, some y that lives between 0 and root 3, and draw a strip, draw a rectangle. And you can just shade that in if you want. So now if you like, you could think of looking at the problem like this, where now you have an independent variable y, but when you revolve this, you have an outer radius and you have an inner radius. So what you generate is a washer. That is, the disk has a portion in the center that's removed. So this is two applications of the disk method. So this is where we don't have to learn a new construct. We just have to apply it twice. So what we can do here is say washer method. And so now what we will have is a outer radius. Sometimes we'll just call that R, uppercase. You can use any letter you like. The uppercase R is good. And we have an inner radius. Sometimes we just run out of letters. We can call that lowercase r. So now it's easy to actually write this. So if you like, you can take this point right here and this point right here and label them. This point will just be 3, comma, y. And the point here, I'll just go ahead and just do an arrow up to that point. This will be y squared, y. So just labeling the points with independent variable y. So now we can look at this and say, well, here's the axis of revolution. The outer radius is constant. It's always going to be 3. So when we take the distance from this point to the axis of revolution, we have r equals 3. And now we want the inner radius. That is, here's the axis of revolution, and here's the actual point here. So let me just do the little curly brace here and bring an arrow down. So now we're going to see that for this particular dimension, and this is what's interesting about this, what is the distance here? Well, we're thinking this point is just 0, comma, y. And then we take the difference in the ordinates and we just get, in this case, y squared minus 0. So in this case, we have little r equals y squared. So this point here, just go ahead and write in the point 0, comma, y. So when we look at the distance here, if you want to think about it this way, this is just y squared minus 0. And let me do a little more focus here. Okay. So this is a left to right construct. So now when we look at this, we're like, okay, well, the distance, the inner radius here, distance is just y squared minus 0, or y squared. And then the outer radius, again, is always going to be 3, regardless of where the y is. So this is where the picture of the region is very helpful. And so now you're thinking, what does the formula look like? Well, we'll just go ahead and write it in terms of the independent variable y. So we would say volume, we'll just write it in general, would be pi, and then we'll just combine the two integrals. Say we have a interval from C to D, and then we would say the outer radius squared minus the inner radius squared. And this, of course, if we're using the independent variable y, dy. So we don't have to create a new formula. We just have to say, if we use the disk method here and then subtract the disk method here. So the difference in the two volumes gives us the desired volume, like thinking about areas bounded by curves. So again, when the region does not abut the axis of revolution, what I usually recommend is just thinking about comparing all of these actual points and just say, okay, we're doing a distance here along the x distance. So how do we measure? So we look at the x coordinates, 3, and then we say, in this case, y squared minus 0. So the idea here is that instead of thinking the distance vertically with x independent, we're thinking the distance horizontally with y independent. So now let's fill everything in. So this implies that our volume, and so we have our pi, and we have our interval of integration, which is 0 root 3. And we can go ahead and square everything. So the outer radius we have is r is 3, so we get 3 squared. The inner radius is y squared, so we have y squared squared. So we're going to find that there's a fair amount of arithmetic with these problems, but the integrals are fairly simple, very, very simple power rule problems. So this will give us a 9 minus, when we square this, y to the 4th power. So, and what you'll find in a lot of these examples, if the lower limit is 0, that will usually simplify greatly the arithmetic that you have to do. So now we get pi. Again, 9 becomes 9y. And then add 1 again, divide by the new power. We get y to the 5th over 5. And we evaluate from 0 to root 3. So again, if you want to turn your paper, rotate pi over 2 radians clockwise to think of this vertically, you can, but you can think of it just like we did with the areas, right and left type thing. It's the same idea. It's just that our minds like to think vertically because we like x as independent. So now we get pi. So let's go ahead and substitute root 3. So we get 9 root 3 minus, and of course here we're going to get 3 to the 5 halves. So we're raising 3 to the 1 half to the 5th power, 3 to the 5 halves divided by 5. And then of course I'll just put a 0 here, because when we substitute 0 into both of these, both terms are 0. So if you like, you can just leave that out. So we have pi, and we have 9 root 3. Now, of course, the 5 halves is just 2 and 1 half. So when we square the root 3, that is, when we think about this, that's going to give us copies of root 3. So think of it this way. When we do 3 to the 5 halves, this is the quickest way to do this. This is just 3 squared times 3 to the 1 half. So this will just be 9 times square root 3. So now this just gives us 9 square root 3 over 5. So you can navigate the fractional powers this way, just so you make sure that you don't overcompensate or undercompensate with that 1 half. And now the 9 root 3's can factor, and we can do a common denominator. So we have pi times 9 root 3, and this will leave us with a 1 minus 1/5. So now we can get a common denominator of 5. So we'll just do a 5 here. So that'll give us a 5 minus a 1. So now bring the 1/5 out. So we have 9 root 3 pi over 5. And of course, now we have a 5 minus a 1, which is a 4. So we can run that over to the 9. So that'll be 36 square root 3 pi divided by 5. Now, these aren't, again, the most interesting problems, but you can see that due to the geometry, we're stuck with the pi. I mean, if we're going to use the disk method, we're going to get an irrational number, an actual transcendental number. So again, these problems marry everything you learned in pre-cal outside of the trig. You have your basic analytic geometry with curves. You're just doing distances. And then, of course, you do your basic calculus, Riemann integrals, and then, of course, the necessary arithmetic. But what we see here is that there is a huge difference here. When we make this solid, we get this volume. When we make this solid, this is going to be a very interesting looking solid, kind of hard to imagine what it looks like. It'll dip down in the middle, so it's going to create kind of a bowl, but have solid outside. So you can think of it designing a building that would be kind of odd shape like that. I guess if you walk toward the center, you have to be really short or just stop, because of course Professor Ron wouldn't be able to walk to the center, or none of us would be. So what we're seeing is that when we change the axis of revolution, we obviously change the solid and we get a very different answer. So one used the washer method, one used the disk method. But again, when we're using disk or washer, the rectangle is always perpendicular or orthogonal to the axis of revolution. Now what I wanted to do was change it up a little bit. Let me pick an example where we actually change the axis of revolution and we can still use our y's. I want to give you some practice with the y's because that tends to be the most difficult for students. You need practice using y as an independent variable. So let's try this one. So let's do the same region. Go ahead and draw the same region, but now we're going to have a different, this is actually part D from your book. And again, we have the same region, y equals square root x equals 3, and y equals 0. But in this particular case, the problem is to revolve about the vertical line x equals 6. So revolve about the line x equals 6. So this just changes the algebra, but the technique is still the same. So let's go ahead and draw this. So I know that the picture gets boring, but the technique certainly doesn't. So we'll spread this out a little bit. So we'll make it large enough to see 1, 2, 3, 4, 5, 6. Just give it a little more space so it's easy to see the algebra and the geometry. So here we have x equals 6. And then, of course, we have x equals 3. And then we'll mark this off. We've got a 1 and a 2. Well, that's a little bit high. Let me spread this out a little bit more to give us a little more room for our square root function. So we'll do like a 1 and a 2. Spread that out a little bit more. And then about square root 3 about right there. So we have a 0, square root 3, y-axis. And now we're going to revolve about the vertical line x equals 6. So you can always draw this in your work. And so we've got this. So remember, we want the distance to the axis of revolution. So if we pick a y, we have to measure the inner radius and the outer radius. So again, notice we have the same interval, y element of 0 root 3. And now, of course, if we square everything, we have x equals y squared. So now I'll just take this to be the y here. It looks like the 1 because it's easy to see. So this will give us the point y squared y. And the same as we had before, this gives us the point. In this case, we've got the y and the 3. So just to plot these 2 points right here. So let me just do an arrow down to here and an arrow down to there. And then we can go ahead and draw in the rectangle for this value of y. Right there. So remember, ladies and gentlemen, this is the axis of revolution. So let me move this over just a little bit. Professor Ron gets in the way. There we go. Yeah, that looks a little better. So now we can see that when we think about this strip, which is perpendicular to the axis of revolution, the inner radius is always constant. It's always going to be 3. So we can say R equals, in this case, 3. Now, if you want, we can go ahead and put in the coordinate pair here, which in this case is 6, y. So when we do the 6 minus the 3, that's going to be the same in all of these cases for the y. So R is 3, 6 minus 3. And now we need the outer radius. So when we look at this, this will be 6 minus a y squared. Now, when you think about these problems, if it's helpful, again, go ahead and coordinatize all these points and then take the difference in the particular direction. So this is the x direction here. And so we need the difference in the x coordinates. So 6 minus y squared. So we have an outer radius of 6 minus y squared, and we have an inner radius of 3. So again, you don't have to guess at this. If you draw the picture to organize your thoughts, it's usually much easier. Now, I will say this. When it comes to doing the area problems, you can think of this like a physics problem or an engineering problem, or like an optimization problem. Like in Cal 1, you probably found the largest right circular cone that you can inscribe in a sphere of radius r. That it really does help to draw the picture and do the cross section. That's an excellent problem in Calculus 1. And so we see that our little sketches do help us out. So now notice we have the washer method. So this implies that the volume will be pi integrated again from 0 to root 3. And now we have the r squared, upper r squared minus the lower r squared. So I'll do a bracket here. So this will be 6 minus y squared, quantity squared, minus 3 squared. So again, the work you do is in the prep work. It's just like doing the area computations. And again, the regions will be of a reasonable nature, that you can do a sketch and you don't have to spend a lot of time with inequalities figuring out which curve is here and relative to the other. So the regions will be reasonable. So now we just need to do the arithmetic and then integrate. So we have pi 0 root 3. Like every step of the problem is important. It's like, you get to this point and then you've got to do your integration. So I just want to make sure it looks nice and clear. There we go. So let's square this. Excuse me. So we get a 36. And then, of course, we get a negative 6y squared times 2. So that's a negative 12y squared. And then if square the y squared, we get plus y to the 4th. And then, of course, minus 9 dy. So now, if you will, we can collect the terms and just write them in descending order. It doesn't matter clearly, but we're creatures of habit. So now we have the y to the 4th. And then we have the minus 12y squared. And then, of course, the 36 minus the 9 gives us a positive 27. So at this point, we're thinking this is just a nice Calculus 1 integral. And all of these problems you could have done in Calculus 1. These again are applications. Again, like I've said many times, you can only get so much done in a particular course. And so the techniques we're using here don't really involve any new mathematics except the definition of the disk and washer method, which are just based on high school geometry. And so now we get pi, let's integrate. So we get y to the 5th over 5, add 1, divide by the new power, minus 12 divided by 3, y cubed, add 1, divide by the new power, plus 27y. So we're back to these radicals again. Excuse me, square root of 3. So now, again, notice the 0 here annihilates all of these. So the lower limit is a blessing. So we have pi. So again, we're going to get 3 to the 5 halves over 5. And of course, the 12 over 3, that gives us a 4. And this will give us 3 to the 3 halves. And then plus 27 times the square root of 3. I do the halves here so it makes it a little bit easier to figure out what you have, at least algebraically. And then, of course, we have the minus 0. So if you want, you can do the bracket here, and then we'll just have the 0 term. Again, when we substitute 0, these are all annihilated. So that's good. We like that. So this gives us a pi. And now, just like we had before, the 5 halves, if you want to think of this, the 5 halves is 2 1/2. And then the 3 halves is 1 1/2. So that gives you 2 copies of 3, 1 copy of 3. So this gives us, in this case, 9 times the square root of 3 over 5 minus 4 times 3 times the square root of 3, the 1 copy and then the 1/2, the 2 copies and then the 1/2, plus 27. Let me not write the radical too soon. 27 root 3. So now at this point, we can go ahead and extract the square root of 3 times 3 from each of these since they all have it. So this will be pi. So we'll have 3 square root 3. Now what's left behind here is a 3 over 5. And then, of course, the 3 root 3 we've taken away. We have the minus 4. And here we take the 3 root 3. So the 3 into the 27 is 9. So that leaves a plus a 9. So I think at this point, this again is calculus 1. Maybe you did some work with the fractional powers in Cal 1. I'm sure you did. And so now we can simplify this. So we have pi 3 root 3. So of course the negative 4 plus the 9 is a 5. So this is 3/5 plus 5. So we can get a common denominator. So we'll do the 5. So that gives us a 3. And of course, 5 times 5 is 25. So we have pi 3 root 3 times 28. 3 plus 25 is 28 divided by 5. So a 3 times the 8 is 24 plus 2 plus 6. That'll give us an 84, right? So 84 root 3 pi over 5. So when we look at this problem, again, I just I set it up so we can multiply this easily. So that's just 90 minus 6, which is 84. then we have the root 3 pi over 5. So again, we see we get a really odd looking answer with these types of calculations. And again, because we're doing the disk and washer methods, excuse me, we necessarily get the pi. So these are transcendental numbers. And so if you're doing an engineering project or you're working with your colleagues, once you become your STEM professional, then it's nice to have an exact answer, which you can approximate one time to get a very nice Google approximation for your colleagues. So again, we want to always look to get a nice exact answer if at all possible, and then we can manipulate that as we need to do our work. Now, what I wanted to do are some other examples here. Here's an example of another region to revolve, and then I want to talk about some cross sections. Now, I will say this, and let me check. Oh yeah, here's a nice example I want to do, Professor Ron. It's like we could meet for longer, but I like to make sure that I cover the examples that are interesting. Okay, so let's do one more example of the disc type washer method. And then I want to say something about cross sections. And then I promised you that problem where we make a ring out of a metal sphere and find the volume of the ring. So that'll be kind of the roadmap here. So example, let's look at this one. It says revolve region about y-axis. Revolve region about the y-axis. And in this particular problem, let's see what we have here. Oh, okay. We've got the following region. Okay, so we have y, this is a little college algebra, square root 3x minus 2. We have x equals 0. We have y equals 0. So we got the y-axis, the x-axis, and y equals 1. Now, again, like we did before, you can look at this. We can go ahead and factor this. 3, so x minus 2/3. So we can see that in this particular case, this is shifted. We could see that this is going to be 0 at 2/3. And then, of course, we're going to make it a little bit bigger because we're multiplying by the square root of 3. So it's going to be extended or stretched vertically. But that just gives us an idea that this is just a nice square root function. So we can get a picture of this. I thought this was interesting because it's a flashback to your college algebra and pre-cal. Now notice, and this is interesting, we can go ahead, we've got our x equals 0, we have y equals 0, and we've got y equals 1. I'll spread this out. So here's y equals 1. So now when we look at this, we can think, okay, well, where do these actually meet up? So I'll spread this out a little bit. We'll have our 2/3 here. And then, of course, we have 1 equals square root. I know this is obvious. You can look at it and see what the answer is, but I thought I'd just do this if the numbers were not nice. So squaring it out, we get 1 equals 3x minus 2. So 3x equals 3. So of course, x equals 1. So you could just stare at that and see that were the case. But so here we've got a 1 here. So that's where we intersect. So when we draw our square root function, it just starts and moves out this way. So there's our square root function. So this is y equals the square root of 3x minus 2. Now, of course, we want to revolve about the y-axis, so we have this. So lots of preliminary work, or it's just the problem. The preliminary work is part of the problem. So now what we can see is when we think about this region, we have the y-axis, which is x equals 0. We have the x-axis, which is y equals 0. We have the radical curve, and then we have y equals 1. So we get this region here. So basically, we use a whole lot of college algebra. And so now when we think about this, this is the disk method, because now we see that the region does abut the axis of revolution. So now, easier problem, right? So we've got a y here that we take and we make our rectangle. So these are fun problems and maybe give you a little bit of break from the tedium of the integrals with the inverse sine and all that. I love integrals, but I know they can get kind of dry after a while. So now, now we think, okay, well, now y is independent. And so we just need the radius function. And so all we have to do is take our equation and solve for x, and then we've got our r that we need. So again, we'll have y squared, again, squaring, equals 3x minus 2. Equivalently, we have 3x equals y squared plus 2. Very simple algebra, but very important algebra. So x now is y squared plus 2 divided by 3. So now when we do our little coordinates here, we have y squared plus 2 over 3 comma y. So now we see that our radius function here, r of y, is just this, y squared plus 2 over 3 minus 0, since that x coordinate is 0. So this, I thought, was an interesting problem where you get a little bit of practice with your college algebra, and then you utilize the technique of the disk method. Again, think of this as like just doing an area problem where you really need to figure out the region, and then the nice clean region will allow you to assess distances to axes of revolution. So now the volume, by definition, and notice here, I'll go ahead and write it in, y lives between what? In this case, 0 and 1. So nice limits of integration, right? So this is the volume, pi, 0 to 1. And now we want to square this. So we have our y squared plus 2 divided by 3 quantity squared dy. So I want you to get practice using x's and y's, and just remember, wherever you choose your independent variable, that dictates the actual variable. So it's not difficult. You don't have to guess. You really don't. And there are times when there's flexibility when you're doing these types of problems. But you just have to make sure that whatever variables you choose, that it makes sense, that it actually describes the region. That's the main thing. Make sure that what you choose does describe exactly what you mean. So now when we square this, of course, we get a 3 squared in the denominator, which we can factor. So that's going to be the 9 downstairs and the pi upstairs, 0 to 1. So we'll square this. So this will give us y to the 4th plus 2y squared plus 4. So what's nice about this particular problem is that the sketch maybe takes a little bit of time, but then we end up with an integral devoid of square roots. So now we get what? Pi over 9, and then add 1, divide by the new power. So I guess we'll get y cubed over 3. So this is 2/3 y cubed, and then of course plus 4y. And then if you want, you can just go ahead and put in the minus 0. It's nice to get used to that, but don't assume it. I mean, there'll be some times when it won't be 0, but I've chosen problems that basically showcase the types of algebraic techniques I want for you. but luckily we've had nice lower limits of 0, so don't count on it because it's not always going to be the case. So now we can do our limits of integration. How nice, 0 and 1. So we get, so in this particular case, let me not jump the gun. I went ahead and evaluated, so let me just kind of move this over, thinking, oh, I'll go ahead and evaluate, but I certainly didn't want to do that. Then I can put in the 0. There we go. So now we have pi over 9. Now we can substitute, and I'll put in the 0 this time. So the 1s here give us nice 1s. So we get 1/5 plus 2/3 plus 4. And then, of course, all the other terms will just be 0. So that's where I needed the 0. I didn't want to do it too soon. Okay, so now we can just do some common denominators. So we're going to have a 3 times a 5. So 3 times 5. So here, this will give us a 3. And then the 5 times the 2, we plus a 6. And then, of course, the 4 times the 15, that'll be a 30 plus 30, or 60. And then, of course, the 0. And so now, when we look here, we get a 9 and a 60. So that gives us a, let's see, there was a, let me check something here. I've got the 4/3. Maybe that was in a different example. Let me just check something here. I've got the 3 and I've got the, oh yeah, I notice here when we multiplied these out, this is a 4 here. I noticed that was kind of small. So when we do the 2 times the y squared times 2, you all probably saw that, but you're just so nice. Thank you. That looked a little small. That's a 4. So let's go ahead and put that in. Yeah, good old algebra. It looked kind of small, and I kept thinking, there we go. So now when we have the common denominator, that'll be a 20. The 4 times the 5. So yeah, that would be a little bit better, ladies and gentlemen. There we go. So now we get the 80 and the 3. So that's an 83. That looks a little better. And then a 15. So this will give us an 83 pi. And then, of course, we have a 90 plus a what? 45. So that's an 83 pi divided by 135. That looks a little better. No, the numerator looked a little small. So remember, when you square this, of course, that's the 2y squared times the 2. So like I said, there's no unimportant step in the problem. So again, what I want to focus on here is the fact that we simply manipulate the equations to give us the correct independent variable. So all steps it's like I were talking to some of the people in Panera Bread, and they said, well, I stopped being a math major when it took more than a half a page to do the problem. I said, well, that didn't take you very far. But they said, well, Professor Ron, I don't love math like you do, but it's true. As you take more and more math, that problems get longer and longer and longer. Okay, so that's a good example. Now what I wanted to do is give you a couple of examples having to do with cross sections, and then we can talk about the finding the volume of the ring. Now the cross-sectional part is very simple. What we want to do is think about, now of course with the cross sections, this is something you can create as an engineer or STEM professional, but we want to think of a particular solid as having well-defined cross sections, and just thinking about, instead of making disc, maybe we're adding up triangular cross sections with thickness. And so with the disc method, we always get the circular disc or the washer. Now we want to change it up to where we decide what the solid will have in terms of cross section, so we have more control. So here's an example. So let's just say we have this. Here's our solid. And we have base of solid is bounded by, there's some nice examples of this also in the lecture notes, bounded by this circle, x squared plus y squared equals 9. And we're going to say that cross sections, so you derive this particular solid. Cross sections perpendicular, so we're going to need to have cross sections perpendicular to a given axis, perpendicular to the x-axis, are squares. And then we want to compute volume of the solid. So this idea is that we have this circle, and then as we take cross sections, it's like you're making a cake that's circular, but all the cross sections are squares. Makes for an interesting building. So when we do this particular technique, we will insist that the cross sections will be perpendicular to a given axis. So let's go ahead and draw our base, which is a circle of radius 3 centered at the origin. So here's our circle, and notice we can look at the upper arc, which will be y equals the square root of 9 minus x squared. And notice we can also use symmetry. We'll be lazy. X element of 0 to 3. So here's our 0. So for instance, if we take a cross section and we just slice in an x here, our square has this edge right here. And we know the area of a square. So if we're going to do this cross-sectional method, we need to have a well-defined area. If we don't know the area, it just kind of falls apart. So now, this particular distance is just 2 copies of the square root. So we have a distance of 2 times the square root of 9 minus x squared. So this is length of edge. And so now you're thinking, okay, so as we take this cross section, the other part of it, again, it actually makes the face of a square. And so to find the area, so we're just going to have a square at each point in the partition and just move along the partition and then add them up with the integral. But because we have this beautiful symmetry here, we can do from 0 to 3 and double the result. So what we're going to do is be lazy and use symmetry. That way we avoid a non-zero lower limit. Use symmetry. So first we need the area formula. So this is what we call the area of the cross section. And so that's just going to be an edge squared. So we say 2 square root 9 minus x squared squared. That's the area of the square. And when we square, we get 4. And of course, the radical is eliminated, 9 minus x squared. So this implies now in general that the volume will just be adding all of the cross-sectional slabs that all have thickness delta x. So the volume will now in general be a to b a of x dx. I think sometimes it's nice to have an example where you motivate the formula, and that way you just don't think you have to memorize formulas. The formulas are kind of a natural evolution of your intuition. So for this particular problem, this implies that the volume, again, we're going to use the symmetry, so we need to double the result. So we'll have 2, 0 to 3, and then our area formula, 4, 9 minus x squared dx. So you're thinking, how simple is this? And this has no pi in it, unless the area formula had the pi in it, which we had with the disk and washer methods. So now we can factor the 4. Again, we love it when the integrals are so simple. 0 to 3, 9 minus x squared dx. So we have an 8. So this gives us a 9x minus x cubed over 3, 0 to 3. Again, the lower limit 0, which annihilates everything. So we get 8. So substituting the 3, 9 times 3 minus 3 cubed over 3. And then, of course, we can just put in the 0 since both of those are annihilated at 0. So this gives us 8. So now we have 9 times 3. And then, of course, here, this is just a 27 over 3. That's also a 9. So this gives us, factor the 9, 8 times 9. And that's a 3 minus a 1. So that'll be a 72 times a 2, which gives us 144. So this arithmetic was a lot easier than the last one. But again, what you do, you're doing the same construct. Instead of having disks that you're adding up like a bunch of pancakes, in this case, we just have a bunch of square slabs that we add up over the interval of integration. So again, this is, say you're going to be an architect and you want to design a building where all the cross sections are squares. I mean, that's pretty standard, but you make it interesting because the base is a circle. And then when people look at it, they have to do a double take. So as an engineer or a architect, or maybe you're working together, you can design a building that has whatever cross sections you want. And then, of course, the other engineers need to know the volume, which you can do your calculus 2 exercise to figure it out. But again, you control the cross section. So this is just simply an adjustment of the other methods we've been using. Now, what I want to do is change this up a little bit. Let's say we have the same base, but we change the cross section. Okay, so this is like the other one. The geometry that you use is based on the actual base, because remember, the cross sections are perpendicular to a given axis, and that base will give you a dimension of the cross section. And then from the formula for the area of the cross section, you can come up with your a of x or a of y, whatever it might be. So in this case, this example, we have the same base. So we'll have, in this case, solid has base bounded by the same circle. We'll say x squared plus y squared equals 9. And in this case, we have cross sections perpendicular, again, we're going to add them up again with the integral, perpendicular to the x-axis, are isosceles right triangles. So that's going to be something we understand. Isosceles right triangles. So the right triangle or the right angle will be in the ceiling, so to speak. And so whatever dimension we have in the circle will be the hypotenuse. So that'll be an easy computation. So let's go ahead and draw this again and proceed just like we did before. So like I say, this is where you're in control and you can think about designing a really interesting building. Like, you know, there are many famous architects have structures around the world that are famous because of their shapes. And so we've got the same circle. We have 3, 3, 3, 3. Yes, drawing the circle in pieces. This is nice to have a French curve. Those used to be real popular, but they kind of fell out of technology changes. No one has a French curve anymore. So now you're thinking that we can use the same analogy with the symmetry. Again, we can take an X, and so we can have one of the edges of the triangle, which will necessarily be the hypotenuse. So this is the same algebra. We have y equals the square root of 9 minus x squared. And so now this edge is 2 copies of the radical. So this is basically hypotenuse of right triangle. Okay, so the idea here is based upon whatever curve forms the base, that gives us the algebra we need. So even though this technique is limited, it does have some merits and it puts you in charge, so to speak. So now what we have here is we're thinking, okay, what's the formula here? So this is the hypotenuse. So and it's isosceles. So we're going to have L squared plus L squared equals H squared. So this gives us the H here. So and it's isosceles, so leg squared plus leg squared equals H squared. And so remember that that's going to be base times height. So when we do A of X, this will be 1/2 base times height. So in this case, we're just going to, the base will be the leg and the height will be the leg. So we just need L squared and we just need to hit it with a 1/2. So what could be simpler? So now this gives us 2L squared equals H squared. So we have 2 square root 9 minus X squared squared. So 2L squared equals 4 times 9 minus X squared. And of course the 2 absorbs, so L squared equals 2 times 9 minus X squared. So of course this implies when we do half of this, the 2 goes away. So this is just 9 minus X squared. And that's our area formula for the cross section. So this, even though it was simpler than the previous problem, you just have to use the geometry that says the edge in the base is necessarily the hypotenuse. So this is an interesting problem. So now the volume, and we'll use the symmetry again, we're lazy, so use symmetry. And if you will, X lives between 0 and 3. So we'll double the result. So now, by symmetry, 2 integral 0 to 3 of the cross-section area formula, which is 9 minus x squared. So again, we're grateful to the simple integrals, dx. So this gives us 2, and this will be a 9x minus an x cubed over 3, 0 to 3. We did the warm-up problem with the inverse sine, and the evaluation was lengthy. Here, we're just doing a bunch of basic arithmetic, which can be difficult, especially if you leave out a factor of 2. So we have to be very vigilant. So we have 2. So we'll substitute the 3. So we have 9 times 3, and then minus 3 cubed over 3. And then, of course, the 0 from the lower limit that we see annihilates everything. So we have 2. So we have 9 times 3, and then, of course, minus a 9. Again, 3 cubed over 3 just leaves us 3 squared, which is a 9. So we have 2 times 9. And this leaves us, of course, here with a 3 minus a 1. So this is an 18 times 2, which is 36. So what's interesting about the cross section, again, just like what we're doing with disk, we add up a bunch of volumes of disk using the Riemann integral. Here, we're just adding the cross-sectional slabs. The cross-section we understand, and it has a thickness delta X or delta Y, depending on the independent variable. So don't look at the cross-section as being anything but very simple. Of course, it's restrictive because we're taking cross-sections that are perpendicular to a given axis. So there, of course, it's very restrictive. But again, it gives you freedom as an architect or an engineer to design a building of your choosing. You just have to make sure that it doesn't fall down. So being an engineer, you would have to have all the nice civil and structural engineers who make sure that the components you use to build it were going to be supportive of the unusual structure. So the geometry that you learn in math is now coupled with your understanding of forces in engineering, so that your structures don't fall down. I'm always happy when I teach future engineers. I said, just make sure that you check your arithmetic. We want that bridge you designed to stay in the air and viable for transportation. Now, the other example, again, that I wanted to do has to do with the ring. That is, there's a WebAssign problem where you basically, you're thinking maybe you work for an industry and you make these rings and you've got these spheres of gold. And you're just going to use the spheres of gold, drill them out to create gold rings. And so, for instance, here's a nice example. So say we have a metal, here's an example, metal sphere. So we start with a metal sphere. So you've got a metal sphere here, and we're going to say that the radius in this case is r. Okay? And what you want to do is drill through the center a cylinder of radius lowercase r to create a ring. So drill a cylinder through the center of the sphere of radius r less than uppercase R. And so basically when you do that, you create a ring. This creates a ring. And what we want to do in this particular case is figure out, using our techniques, in this case, the washer method, the volume of the ring. So compute the volume of the ring. So this would be like a formula that you were doing in physics. So what we can do is draw a picture of the cross section of the ring and now forget how we made it and treat the ring as a solid of revolution. So the key is treat the ring as a solid of revolution. So just like we know, the physics and the math fit together if we can get a nice model. So we can now think of this as a solid of revolution. So let's do a nice cross section of the metal sphere. So now what we have, we've got this R here, and we've got like a minus R here. And then we basically have this cross section, which is going to define what we bored out, the cylinder of radius lowercase r. So here's the ring here. If we revolve this, we create the ring. So now we're going to think of this ring as a solid of revolution where we do this. Okay. So this, we're thinking, okay, so this distance here is r. That's the radius of the sphere, excuse me, of the cylinder, where we drill a cylinder through the center of radius little r. And then, of course, the outer curve here, and we're just going to we'll pick an x here. So we've got r. We'll draw in our rectangle. And then the outer curve here, we can just use the equation of the circle. So this will be r, or excuse me, y equals the square root of r squared minus x squared. And of course, we're going to use symmetry again. So in this case, x lives between 0 and r, at least for now. But we're going to have to figure out this. So we've got the 0 here, but then what's question mark? We need to stick that in. So let me give a little extra space here. So here we have an r, but we need the x coordinate. So in this particular case, we say, okay, so what goes here? So we've got what r equals the square root. You can kind of do this in your head, r squared minus x squared. So here's the circle, which defines the metal sphere. So we get r squared equals r squared minus x squared, and just flip things around. So we have x squared equals uppercase r squared minus lowercase r squared. So this would imply, if we want the x right here, we'll take the principal square root. So now that's what goes here. So this will be the square root of r squared minus lowercase r squared. So again, we will use symmetry. So we can actually revolve this piece here, and I'll go ahead and draw this in. The outer radius, big R, is just this. So this is real simple, not as difficult as some of the other problems we've done. So when you think about this particular exercise and you think about what we have to do, we have an outer radius and inner radius. We've now figured out the values here. So as we come down here, that gives you the value of x, which we wrote right here, square root r squared minus lowercase r squared. Okay, so again, when you look at this setup here, it looks a whole lot more complicated than it is. That's why I did the base with the circles, to get you thinking about circles. And now you can see that even though we described the process of making the ring from an engineering standpoint, from a mathematical standpoint, we now describe the ring determining the volume in a completely different construct, as basically a solid of revolution with an inner radius and outer radius. So now we'll use the symmetry. So this implies that the volume, again, we've got our 2 from the symmetry, and then of course we've got the pi. So here, just write, I don't always write this in, but that's symmetry. And then we have, of course, 0, and I'll do this, I'll just do the 1/2. So we have r squared minus lowercase r squared to the 1/2. And then we have our outer radius, so I'll use the brackets. So outer radius, r squared minus x squared, squared, minus inner radius, little r squared, dx. So now we're thinking, wouldn't it be nice if all the problems were this simple? Of course, the setup was a little bit more complicated, but you can see that the algebra is very straightforward, and it's doable. So now this gives us 2 pi integral 0 r squared minus little r squared to the 1/2. And then of course the squares absorb here, or the radicals absorb. So this gives us r squared minus, I'm just going to go ahead and stick the, well, it doesn't matter. We can change the order as we need. We get this. Now remember, the r's are constant, so they just get an x with them. So I'm going to group them together, so it's going to make it easier to evaluate. So now we have 2 pi. And again, we get an r squared x and a lowercase r squared x, but I'm just going to write them together. So I'm just going to say r squared minus little r squared, or lowercase, times x. Just group those together because it's going to make it easier to evaluate. And then, of course, this will just be minus x cubed over 3. 0 r squared minus lowercase r squared to the 1/2. So again, remember, we just get r squared x minus lowercase r squared x. And so what I do is just, I group them together, because you can see that these are just going to combine, and that's going to make the algebra easier. So now notice another thing, and like, we can't seem to get away with it, but we're not going to complain. The lower limit 0, again, will annihilate all of this. And so we don't have to worry about that. So this will give us 2 pi, and we'll go ahead and substitute. So this will be r squared minus lowercase r squared times the radical. So this will be r squared minus lowercase r squared to the 1/2. And then of course here we'll get minus, and then we'll just, that's why we're doing the radicals before. There's a reason to help you out with this problem. So this will be r squared minus lowercase r squared to the 3/2 divided by 3. So what we're seeing here, even though we have the big R and the lowercase r, that seems to drive the problem. That seems to be really the only thing that's driving the problem at this point. And now we've got the same factor. We have a 1/2 plus a 1. So we have a 3/2 power of this base, and we have the 3/2 power here. So now we can factor that. So we can see that combining these two was a help. So this gives us 2 pi, and we have r squared minus lowercase r squared to the 3/2, and that leaves behind a 1 minus a 1/3. So we can do a common denominator. So we have 2 pi r squared minus lowercase r squared to the 3/2. And we'll just do a 3. And then, of course, this will be a 3 minus a 1. So what I try to do is set up the algebra in a way that when we get to a derivation, we're basically doing all of the same tricks. We're doing the algebra, we're doing the symmetry, we're doing the inner radius, the outer radius, all of the same components that we've done before. And so now we just get a 2/3 here. So this will be 2 pi r squared minus lowercase r squared to the 3/2 times a 2/3. And so we can just move all of that up front. So that'll be a 2 times a 2. So that's a 4 pi over 3 times r squared minus lowercase r squared to the 3/2. So this gives you a nice generalized formula for making a ring from a metal sphere. I mean, when you think about it, and I mean, a lot of you are, you're very intuitive when it comes to engineering, and maybe computer science and finance and things like that. That's why you're in STEM. But I would say that a large proportion of you have some interest in the engineering field. As I teach pre-cal and calculus, I tend to get most students interested in the STEM field that involves engineering. And so what's neat about the calculus is that we can derive all these interesting formulas that now make this computational. So if you wanted to describe a particular process, it's like, well, how much gold do I need if I'm going to, make a ring from this? How much of this metal sphere will actually be in the ring, so I can figure out how much to charge for it. I mean, I guess jewelers have to be somewhat skilled in mathematics so that they actually, make money. But they have different ways. They might look at the gold in terms of weight, not so much of volume. So everybody has methods and conventions that help them to do their work. So again, what I want you to realize with this example is that we treat this from a engineering standpoint, and then we say, okay, once we have this ring, can we transform the solid production into a mathematical model that we understand? And so once we describe this, you just have to kind of divorce yourself from the engineering standpoint and then say, oh, this is really a solid of revolution. So I want you to spend some time just going through the basic construct here and convincing yourself that this is really no more difficult than some of the problems we did with the square roots and all. And again, take stock of all the different types of techniques that we use. Remember, and this is important, when you think about where we started, we think about a very simple example where we have the region abutting the axis of revolution. And then we think about an instance where we don't think about a particular problem in terms of the disc or washer method. We think about it in terms of a cross section, which we prescribe. Okay, so very restrictive. And then we say, okay, well, let's just take this example and model it to something that has some kind of relevance in our own society. So I want you maybe to think of what we've been doing for the last couple of lectures, basically with the areas and the volumes of the solids of revolution as just being very practical mathematics. Now, of course, the original example here, again, I want you to go back and review this so you just get some practice with the inverse sign. Again, I made this up so that the numbers are a little bit more hideous than maybe you would get from a refined computer algebra system, but again, a very good example. And so what we're going to do as we move into the next section is continue with the volumes of the solids of revolution, but we're going to introduce another technique called the shell method. Now, that's not intended to make it more difficult. It just provides another method that may be doable when the disk method does not work as well. And again, not a source of confusion, just another technique. And then as we finish up the chapter, we'll talk about arc length, uh, areas of surfaces of revolution. We're going to talk about center of mass. So as most calculus students think of chapter 7 in Larson, they think of very practical mathematics. Practical mathematics you'll use as an engineer. And then of course, after that, we'll do some more integrating. But just reminder, I will have a conference hour today at 11. Of course, on Thursday, I've got 3, too many, but they're used. So please stop by if you have questions. Remember, the first homework set is due this evening at 11 p.m. and then your first quiz is due at 11 p.m. tomorrow. So if you have questions that you want to ask today or tomorrow, please stop by the conference hours. I'll send out, of course, the email invitations. Again, I'm not trying to barrage you with a bunch of emails. You probably say, well, there's another conference hour, but I want it to be available to you. So it's in your inbox and it's like, well, I have a question. Let me go to Professor Ron's conference hour at this time. So just use that as a convenience. If you don't need it, just ignore it, hit delete or whatever. But again, I want you to be able to come to the conference hour with ease. And of course, the Zoom is our mode of communication. So I appreciate your attendance today. Let's enjoy the cooler weather once it gets cool inside. And so if I don't see you at the office hours, I'll look forward to getting some messages from you on WebAssign. So everybody have a great day and I'll talk to you soon.